2 matrix A, B, C, D, what's the quantity A minus D called? The trace. And what's the quantity AD minus BC called? Determinant. Okay, and then this is a sketch of the trace determinant plane. What kind of eigenvalues show up within the parabola? Yeah, imaginary or complex. I'll take either one. Yeah. Okay, so we're going to spend a little time sort of summarizing into a table everything that we know about linear systems, what their solutions can look like, what that means about the eigenvalues, what we call that kind of system. We'll do a few together, and then you can finish filling it out on your own at some point. But it'll be a good exercise to sort of put everything summarized in a table format. And I've also left out a few special cases that you don't really need to be concerned about. So. Okay, a sink. What kind of eigenvalues give you a straight sink? Negative, real, right? Right, and a typical phase portrait has got 2 straight line solutions. Just draw them in randomly, right? And then the rest of the phase portrait will start, each solution will start parallel to the eigenvector that's associated with the eigenvalue further from 0. Okay, so let's just pretend this is lambda 1, which is -8, right? And this is lambda 2, which is -2. Okay. So a straight line solution that goes with the -8, all my solutions that I draw in here are going to start parallel to the -8 and come in tangent to the -2. So it would look like that. And I need arrows, everything going in. And then you just draw that in every quadrant. Parallel to the -8, come in tangent to the -2. So there's a typical phase portrait. And then solutions, x of t and y of t, graphs of solutions. So this is x and y, and this is t. So what do my solutions generally look like? What are they all doing? Yeah, they're all just coming towards 0. Yeah. Wherever they start, they're just approaching 0. So like something like this. And x might start closer, but it does the same thing, it just goes to 0. All right, what kind of system has real, distinct, positive eigenvalues? Source. I should have put distinct up here too. They need to be 2 different eigenvalues to get a sink. Okay, so my typical phase portrait is going to look just like the phase portrait I drew up here, except all the arrows are going to point out. And again, it's going to be tangent. They're going to leave the origin tangent to the eigenvector that's closer to 0 and end up parallel to the one that's further from 0. So put in my random straight line solutions. And let's just say that this one is lambda 1 is 2. This one's lambda 2 is 8. So as my solutions leave the origin, they're going to leave tangent to the smaller one and end up parallel to the bigger one. And then if I wanted to draw solutions as functions of time, well, all my solutions start at 0 and just grow. Right, so. All right. What phase portrait? How do we classify that phase portrait? Saddle. And what do we know about the eigenvalues of a saddle? One positive, one negative. Yeah. Real. One positive, one negative. Different. So if one's positive and one's negative, they would have to be distinct. That's why I didn't write it. All right, and then what do the solutions for a saddle look like? So let's say my initial condition is 1 or 2, 1, something like that. So x starts at 2. And what's it going to do from there? What's x doing? X is getting smaller, right? Moving to the left. So x is getting smaller. And then y is starting at 1, right? But y is going to go up to infinity. Okay, spiral sink. What kind of eigenvalues lead to a spiral sink? Complex. Yep, that makes it a spiral. What makes it a sink? What has to be negative? The a. Yeah, the real part of your complex number has to be negative to get a spiral sink. And so your phase portrait, typical phase portrait, just looks like this. Spiraling in towards 0. And your solutions are going to spiral, but what's changing? Each time we go around, the max and mins are getting smaller, so the amplitude is going to diminish. So this is t, x and y. So it might look like this. Approaching 0. And then your y would look something similar. Let's see, if that's my initial condition, then x started high and went around, and y would start low, and oops, I need the same amplitude. Well, you get the idea. Just a qualitative picture. All right, so what if the reverse happens? What if I have something sinusoidal, looks like it's sinusoidal, but my amplitude is starting really small and getting bigger and bigger and bigger? Spiral source. And in that case, my eigenvalues are complex, right? They look like a plus bi, but the a value has to be positive. The real part has to be positive. And then my phase portrait is just spiraling out from the origin . All right, what kind of system has strictly imaginary eigenvalues? A center. Right, so its phase portrait is concentric circles. And you would just need to know, you would pick like one point in the phase plane and find a vector at that point to tell you what direction it is circling in. I'll just put these, this is random. Yeah, they all go the same direction. All right, and then what do the solutions look like when you have a spiral? Yep, it's sinusoidal, constant amplitude. All right, look at this solution here. It kind of looks like it wanted to oscillate, like it went below and then, but it never sort of finished oscillating. It just petered out and went to 0. That's the repeating eigenvalue. That's the boundary between a spiral sink and just a sink, right? A sink would just go directly to 0. This has like sort of an almost sinusoidal thing happening. So this is a repeated positive or negative eigenvalue. Negative, why? Yeah, it's a sink. It's going to 0. Repeated negative eigenvalue. And this doesn't really have a name. I call it the boundary between sink and spiral sink. All right, and then it's phase portrait. These guys just have one straight line solution because it only has one repeated eigenvalue. So you put in a random straight line solution, and then everything starts out and parallel to it and comes in tangent to it, to the same eigenvector. So it will be like this. Yeah, starts out parallel and then comes in tangent to the same line, like that. All right, my next phase portrait underneath that one looks almost exactly the same, except everything's going out. So this is, yeah, so these are repeated positive eigenvalues. And it's the boundary between a source and a spiral source. So my solutions are going to look sort of the opposite of this. A source would start at 0 and just go up, but a spiral source is going to start at 0 and maybe like do something like that. Or, yeah, I think that's actually it. Because it can't cross the equilibrium, so it's got to just something like that. All right, so those are like the main types of systems you can have. And then the cases with 0, I'm going to leave you to finish on your own at some point. So we did this on last week, Monday, or I don't remember, Wednesday maybe. So you can fill those in on your own later. Okay, so now we're going to talk about the trace determinant plane. So making that table is one way that you can organize all your information about linear systems. But we have this other graphical way called the trace determinant plane. So let's look at a random linear system that just has A, B, C, D, like a generic 2x2 matrix. So I want to find the characteristic polynomial. So remember that's A minus lambda times D minus lambda minus BC. That's my characteristic polynomial. If I wrote equals 0, that would be called the characteristic equation, right? So if I just say characteristic polynomial, it just means this. All right, now I'm just going to multiply everything out, and I'm going to put this in my typical quadratic form, like my something x squared plus something x plus a constant. All right, so if I distribute this all out, I get AD minus A lambda minus D lambda plus lambda squared minus BC. All right, so I only have one lambda squared term. So I've got lambda squared. And then my lambda terms, I have minus A lambda and minus D lambda. So I have minus A plus D lambda. That would be minus A lambda minus D lambda. Okay. And then finally, my constant terms are AD minus BC. So I'm going to just put this all in one color. Okay, so lambda squared has no coefficient, and then the coefficient on lambda is A plus D, and we typically call that the trace, or T for short, right? And AD minus BC, we're already familiar with that quantity. Oh, how did I mess this up? Yep. Yeah, you're right. You're right. A minus D, right? But they're supposed to both be negative. AD minus A lambda minus D lambda. So A plus D is the trace. Okay, sorry, typo. And in the quiz, it was A plus D, so make sure you change your score if you marked it wrong. Okay, so my trace is, no. Oh, right. Oh. All right, let's throw that question out. Everybody gets a point for that question no matter what. All right. So A plus D is known as the trace, call it T. AD minus BC, we've been familiar with that quantity for a while. It's the discriminant D. I was going to give a little disclaimer in the I've only taught this class once before, and the last time I taught it, I left this section out, so this is my first time teaching it. So there's bound to be some mistakes. Okay, so I'm going to rewrite my characteristic polynomial, but instead of that A plus D, I'm going to use a T, and instead of AD minus BC, I'm going to use D. So this is just going to become lambda squared minus the trace times lambda plus the determinant. All right, so then I want to solve the characteristic equation, which means set that thing equal to 0. I want to solve it for lambda in terms of T and D. So if I have that equal to 0, then lambda is going to be the opposite of B, right? And in this case, B would be negative trace. So this becomes T plus or minus the square root of T squared minus 4 times 1 times D, all over 2. So we just did the quadratic formula on the polynomial up there. All right, so we can classify the equilibrium points just by knowing the trace and the determinant, right? So I could say, well, if T squared minus 4D is equal to 0, I'm going to have repeated eigenvalues, right? If T squared minus 4D is negative, I'm going to have complex eigenvalues. If T squared minus 4D is positive, I'm going to have real distinct eigenvalues, so I'd either have a sink or a source. So I can do my entire classification if I just know the trace and the determinant. Oh, I just told you the answer to this. What restrictions on T and D result in repeated eigenvalues? What did I say? Yeah, T squared minus 4D equals 0. If the thing under the square root is 0, then t plus 0 and t minus 0 give you the same thing. So you're going to have a repeated eigenvalue. So then we create this picture called the trace determinant plane. And you just graph this parabola, t squared minus 4d equals 0. And that blocks off, that's the boundary, right? That's the repeated eigenvalues, right? That's the place where t squared minus 4d is 0. And remember, repeated eigenvalues are the boundary between spiral solutions and sinks and sources. What? Yeah, like if you cross this line, in here you have one kind of solution, and out here you have a different kind of solution. On the line you have repeated eigenvalues, yeah. All right, so let's see what's in here, right? Like, is t squared minus 4d going to be less than 0 or bigger than 0 if you're within the parabola? So let's pick a point. Like, here's a point in here, like 0, 4, right? That's 0, 4. That's a t and a d, right? This is the trace determinant plane. So if I put 0 in for t and 4 in for d, I get something less than 0, right? I get a negative. So within here, I have all complex eigenvalues. But within the category of complex eigenvalues, there's two possible phase portraits. You could have a spiral source or a spiral sink. So if we go back up to my quadratic formula up here, it's the real part, right? The t squared minus 4d is negative. That makes it spiral. It's the real part that's going to tell you whether it's a source or a sink. So that t, the trace, if the trace is positive, you're going to get a spiral source. If the trace is negative, you're going to get a spiral sink. So to the right of the d-axis, that's where t is positive. So over here, we have spiral sources. And when t is negative, we have a spiral sink. Okay, everywhere else in the trace determinant plane, we have real eigenvalues. Okay, it's only within the parabola that you get complex eigenvalues. So everywhere else, they're real. So let's look over here where the trace is positive and the determinant is positive. Right, pick some random point over here, like 1, 2, 3, 4, 5, 5, 1, or 4, 0. Well, 0 might be its own special kind of thing because it's when the determinant is 0, you might get something special. So I'm picking something like 5, 1. So if I choose 5, 1 and put it into my eigenvalue formula, 5 for t and 1 for d, I would get 5 plus or minus the square root of 5 squared minus 4 times 1 all over 2. Radical 21, what is that approximately? I should have picked numbers that gave me a perfect square. I don't know. Between 4 and 5? Between 4 and 5. So if I do 5 plus that, I'm going to get a positive, right? And if I do 5 minus that, I'm also going to get a positive. So these are both positive, right? Because radical 21 is smaller than 5, so you're going to get a positive whether you add or subtract. So if both eigenvalues are positive, that tells you that over here we have a source. So both eigenvalues are positive and real. We have a source. So now, what do you predict is going to happen over here? It's going to be a sink, yeah. Yeah, and you could pick a point, get the eigenvalues just to verify, but this is going to be a sinc. And this kind of makes sense because this line is the boundary between spiral source and source, right? And over here, it's the boundary between a spiral sinc and a sinc. All right, what about below the t-axis, though? What about when the determinant is negative? Like, pick some point in here, like, let's say 4, -1. Right, if I get the eigenvalues there at 4, -1, what? You have 2 real for 4, -1? Let's see, so so I have 4 plus or minus the square root of 16 plus 4 over 2. Radical 20, what's that approximately? It was 21 before, it wasn't. .47. It's bigger than 4, right? So if I do 4 plus 4.47, I'm going to get a positive. If I do 4 minus 4.47, I'm going to get a negative. So this is one real positive, one real negative. That makes a saddle. So I think, I can't remember, but I think that this whole lower part is saddles. Yeah. Yep. All right. And then this line itself, that was repeated. Remember, repeated eigenvalues. Over here, they're repeated negative eigenvalues. Over here, they're repeated positive eigenvalues. Over here, when you're on that line, you have repeated positive. If the trace is 0, go back up to the formula for the eigenvalue. If the trace is 0, what kind of eigenvalues do you get? Be more specific than complex. If the trace is 0, that term goes away. It's a center, yeah, which means strictly imaginary. Yeah. Yeah. So when you're on the d-axis here, so your trace is 0, this axis is centers. Which makes sense, right? Because it's the line between a spiral sinc and a spiral source. Only positive that axis. That's a good question. What if d were negative? Yes, because if d were negative, this would be -4 times a negative number, which would give you a positive number. So you would have 0 plus or minus some positive number. So it would be a saddle. Yeah. 0, 0 is a special thing too. Yeah. Let's look at what happens at 0, 0. If I put in 0 for both t and d, you end up with lambda is a repeated 0 eigenvalue. So your eigenvalues are 0 and 0. And that's a special case that we looked at briefly in the class activities, but this is 0 repeated eigenvalue. And anytime the determinant is 0, right? If you're on the t-axis and the determinant is 0, right? If you got rid of that d, this says t plus or minus t, right? So you're going to have one eigenvalue, t plus t over 2, and your other eigenvalue, t minus t over 2, will be 0. Yeah. So these are, this axis represents a 0 eigenvalue. And it would be a negative over here, and over here you would have, oh sorry, I mean the other one, not the one that's 0. The other one would be negative, and this one has a 0 eigenvalue, and the other is positive. So this is just a classification scheme, right? So if you calculate the trace and the determinant of a 2x2 matrix, you can determine where in this picture your trace and determinant falls, and then you would immediately know what kind of system you're looking at. That's it.